Stars are the most fundamental building blocks of the universe, providing the light, energy, and elements necessary for life as we know it. The study of stars and their evolution, known as stellar evolution, is a central topic in astrophysics. Over the course of a star's life, it undergoes a series of stages that transform it from a simple cloud of gas and dust to a dying remnant, sometimes culminating in a white dwarf. This description will explore the process of stellar evolution and the nature of white dwarfs, their formation, properties, and their role in the broader cosmic picture. Stars are born in vast molecular clouds, also known as stellar nurseries, where gas and dust are densely packed. These clouds are primarily composed of hydrogen and helium, and they are often several times more massive than our Sun. The process begins when a disturbance, such as a nearby supernova explosion, causes a region within the cloud to collapse under its own gravity. As the material collapses, it heats up and the density increases, leading to the formation of a protostar. A protostar is not yet a fully fledged star, but it is the precursor to one. During this stage, the gravitational energy of the collapsing material is converted into heat, and nuclear fusion reactions begin in the core. The fusion of hydrogen atoms into helium releases vast amounts of energy, which marks the transition to the main sequence phase of a star's life. The main sequence is the longest and most stable period in the life of a star. During this phase, the star burns hydrogen in its core through nuclear fusion, maintaining a balance between the gravitational forces trying to collapse the star and the outward pressure generated by fusion. The Sun, for example, is currently in its main sequence phase, where it has remained for approximately 4.6 billion years. The duration of this phase depends on the mass of the star. More massive stars burn through their hydrogen fuel more quickly than smaller ones. Stars on the main sequence fall along a diagonal band on the Hertzsprung-Russell diagram, HR diagram, a graphical representation of stellar luminosity versus temperature. The position of a star on the diagram can provide insights into its size, temperature, and luminosity. The Sun, for example, is a G-type star, which means it is yellow and has a surface temperature of about 5,500 degrees. In contrast, hotter stars, such as those classified as O or B-type, are blue and more luminous. As stars exhaust the hydrogen fuel in their cores, they begin to leave the main sequence and enter the red giant phase. The core contracts under gravity, causing the temperature to rise, while the outer layers expand and cool, giving the star its red color. In stars like the Sun, the core becomes hot enough to initiate the fusion of helium into heavier elements, such as carbon and oxygen. The red giant phase is marked by the shell fusion of hydrogen surrounding an inert helium core. This process increases the star's luminosity and size dramatically. In the case of the Sun, it is predicted that, in about 5 billion years, it will expand to become a red giant and engulf the inner planets, including Mercury, Venus, and possibly Earth. For low and medium mass stars, the red giant phase is followed by a series of complex processes, culminating in the formation of a white dwarf. After the star has exhausted its core helium, it can no longer support fusion reactions. In the case of a star like the Sun, the core will contract, and the outer layers will be expelled into space, creating a planetary nebula. The core that remains is what becomes the white dwarf. The process of a star shedding its outer layers during the red giant phase is crucial. It releases a significant amount of material into the interstellar medium, enriching it with elements such as carbon and oxygen, which are later incorporated into new stars and planets. These expelled outer layers form the planetary nebula, which is a colorful and often intricate cloud of gas and dust. Once the outer layers are expelled, the remaining core is incredibly dense and composed mostly of carbon and oxygen. This dense core, which no longer has the fuel necessary for fusion, becomes the white dwarf. A white dwarf is a remnant of a star that has exhausted its nuclear fuel, but has not undergone a supernova explosion, as it is too small to trigger such a catastrophic event. White dwarfs are some of the most intriguing objects in the universe. They are typically about the size of Earth, but contain the mass of up to 1.4 times that of the Sun, making them extremely dense. A white dwarf is supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that arises due to the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. This pressure counteracts the force of gravity trying to compress the star further, preventing it from collapsing into a black hole. Despite their small size, white dwarfs are incredibly hot when they form, with temperatures often exceeding 100,000 K. However, since they no longer undergo fusion reactions, they gradually cool over time. The cooling process takes billions of years, and as they cool, they dim and become less luminous. Eventually, they may fade to the point where they are no longer detectable, becoming what is known as a black dwarf. The mass of a white dwarf is typically less than about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. If a white dwarf's mass exceeds this limit, it can no longer support itself through electron degeneracy pressure, leading to a catastrophic collapse, potentially resulting in a type Ia supernova. In some cases, white dwarfs are found in binary systems, where they have a companion star. In these systems, material from the companion star can be transferred to the white dwarf through a process known as accretion. As the white dwarf accretes material, it may exceed the Chandrasekhar limit and undergo a thermonuclear explosion, resulting in a type Ia supernova. This process is important for cosmology, as type Ia supernovae are used as standard candles to measure distances in the universe. Binary systems also provide an opportunity to study the properties of white dwarfs in more detail, as the interaction between the two stars can affect the evolution of both. In some cases, a white dwarf may accrete enough material to become a nova, a sudden outburst of light and energy caused by the ignition of hydrogen on the surface of the white dwarf. White dwarfs play a significant role in the evolution of stellar populations in galaxies. Since they are the end state of low to medium mass stars, they contribute to the overall mass and evolution of galaxies. In fact, white dwarfs represent the most common end state of stars in the Milky Way and other galaxies. They are thought to account for a significant fraction of the stellar population in the universe. The study of white dwarfs can also provide valuable insights into the history of our galaxy. By examining the age and cooling rates of white dwarfs, astronomers can estimate the age of the stellar populations in different regions of the galaxy. This information is important for understanding the formation and evolution of galaxies over cosmic time. Stellar evolution is a complex and fascinating process that explains the life cycle of stars, from their birth in molecular clouds to their eventual death, as white dwarfs, neutron stars, or black holes. The formation of white dwarfs marks the end of the evolutionary path for low and medium mass stars, and these remnants provide valuable insights into the past, present, and future of the universe. As we continue to study these enigmatic objects, we will gain a deeper understanding of the forces that govern stellar life and death, as well as the broader dynamics of galaxies and cosmic structures.